Okay, so we get to look at now a very interesting application of derivatives, really, and that is the so-called Newton's method, named in honor of Isaac Newton. And this method is a method for basically finding the roots of a function, which can also be used to find the solution to equations. You may have an equation solver you know how to use on your calculator, for instance. If you plug in an equation and it can give you the solutions to the equations, of course numerical estimates, not the necessarily exact answer, but numerical estimates of those. And so how does the calculator do that? Well, we looked at the bisection method quite a while ago. Bisection method is a way of sort of zeroing in, if you will, by knowing, like, here's a function here and it crosses the x-axis here. It's kind of like we can know that since the function is negative here, for some value back here, and positive from some value over here, assuming it's continuous, there's going to be a solution somewhere on that interval, and we just kind of pick the midpoint and then keep making smaller and smaller intervals that contain that solution, and we can keep that process going. So that's the bisection method, essentially. Newton's method, though, is a little bit faster convergence, and it's really the beginning of a whole set of other so-called iterative methods to help us estimate solutions to equations and roots of functions. So let's suppose this is the graph of the function f, and I'm trying to find the zero, or the root of that, right? Basically where it crosses the x-axis here. Now I've turned off the scaling here, or the labeling. You don't really know what the distance is between each of these tick marks, and that's not the important part right here. But clearly we're trying to find what this value is. What's the value of x, right? If this is the y-axis, then in this case it's probably some negative value of x. This is an iterative method, and it makes use really of the derivative, and in particular the tangent line. And so suppose I didn't know what the solution was, but I guess a value. Okay, just guess any value of x. There's infinitely many to choose from. Maybe I'll choose this value right here, and I'm going to call this initial guess x with a subscript 0. Okay, sort of my starting point. Right? And if I have the actual function, I can plug this value in, and I can clearly see this is not the 0 because the output to the function is some positive value, right? I can come across here and get that value, right? So it's not the 0, and you can clearly see it's not. It's too far to the right of the actual 0. But now what I'm going to do from that is I'm going to, at this point, since I know the function, I can find the derivative, and I can find the slope of the tangent line at that point. And let's do the tangent line just touching the graph. The bottom of my ruler just touches the graph right at that point. And so let me go and sketch that tangent line here. Right? So this is the tangent line. And what is the slope of this tangent line? What is the slope of this tangent line? Well, it's the derivative of the function f at this point. So it's literally f prime of x sub 0, right? That is the slope of that tangent line. And furthermore, I know the point here is the point x sub 0 comma f of x sub 0. Right? We know that. Again, input, output. And so we know that point, we know the slope, assuming again we know the function, we can find the derivative and get the slope of that line. Okay, so what we're going to do is we're sort of going to ride the tangent line. So we're up here, we're trying to look for the 0, it's not here, this is not the 0 of the function, right? But I'm going to get on this tangent line and I'm going to slide down. Whee! All right, just like going down a slide until I hit the x-axis. And where that hits, that is going to be my first iteration, if you will, of this process. And I'm going to call that value where it touches the x-axis x sub 1. Okay, so I start at x sub 0, get on the tangent line, and go to x sub 1. I want you to notice something. Okay, remember we're trying to get the true value of the root, which is right at the top of my pen, right there where it crosses the x-axis, right? My initial guess x sub 0 was obviously not it. But notice my new guess, my first iteration, is a little bit closer. It's a little bit closer. How can I find the value of x sub 1? How can I find the value of x sub 1? Well, let's see how to do that. I know the equation of this green line. What's the equation of that green line? What's the equation of that tangent line? The point that we know is x naught comma f of x naught, and I know the slope is f prime of x naught. And so the point slope form of the equation is what? Y minus the y coordinate of that point, which is f of x sub 0, equals the slope. What's the slope? That's the f prime of x sub 0 times what? X minus the x coordinate that's given, x sub 0. So I'm just putting this into point slope form. Again, it's a lot of symbols in here, but keep in mind this is if we know the function f and I know x sub 0, then I'm going to be able to find this is going to be a number, the slope of the line, f of x sub 0 will be a number, and x sub 0 will be a number. X and y really are the only variables, so to speak, and that's the variables that represent every point on this tangent line. Okay, so that's the equation of the line. But in particular, to find x sub 0, what do I need y to be? What's the y coordinate? What's the y coordinate? The y coordinate is 0. So if y is equal to 0, then the value of x in this equation must be x sub 1, right? Because that's the coordinates of that point. It's x sub 1 comma 0. So if y is 0 in this equation, x over here has to be x sub 1. And what do I get when I do that? Plugging in 0. 0 minus that is just minus 1 times f of x sub 0. F prime x sub 0, and then what do we say? X has to be what? x1 minus x sub 0. Now, I'm looking for what's the value of x sub 1. Well, here's x sub 1, and remember, we know x sub 0. That's given. So everything else I know, I just don't know x sub 1. Solve this equation for x sub 1. How do I do that? So it's this derivative times this difference. So let me divide by this derivative, both sides of the equation. And then to solve for x1, what do I need to do? Just add x sub 0 to both sides. And when I do that, I'm going to swap sides here. I'm going to put x sub 1 over on this side. But when I add it to this, I'm going to write this as x sub 0 plus a negative or minus this fraction. Okay. And there it is. There's the value. So I can find the value of x sub 1, right, given the value of my initial guess, x sub 0. So I go up, I ride down this tangent line till y is 0 and y is 0, right? I know x is x sub 1, plug that in, and then I can solve. So if you know x sub 0, and you know the function, and you know its derivative, you'll be able to calculate this, and you'll have your x sub 1. Okay? So where do we go from here? So we're still not at the solution. Well, we're going to do the same thing. In other words, I'm going to start at this point now and come down to this location for this point on the graph, right? Again, x sub 1 is not the 0 for the function because its value is some negative value. In fact, the coordinates are x sub 1 comma f of x sub 1, right? And then what do? We're going to ride the tangent line again. So what's this tangent line look like? There's a lot going on here. Let me try and draw this in purple. So if I just touch the graph of that function just to get my tangent line, there it is. And so let's sketch that tangent line. Okay, so this time I'm going to ride up the slope, ride up the slide. I got to go against gravity here, I guess. So from this point I go up and I hit the graph right there. I mean, the graph of the function is curving away slightly there. This purple line is straight, but it's hard. It looks like they're the same. If we were to really zoom in real close on that, we would see a slight difference though, right? So my point I'm hitting here, that's going to be my x sub 2, my second iteration. And I want you to know x sub 2 is really close to that 0, isn't it? Probably not right on it, but it's pretty darn close. Okay? How do I get the value of x sub 2? Well, this purple line that I've drawn, this tangent line, is going to look very similar to this right here, but instead of x sub 0, right, comma, f of x sub 0 being the point, here's the point, x sub 1, f of x sub 1, and the slope here is f prime of x sub 1. So basically it looks very similar to this, except replace x sub 0 with x sub 1, right? And now to find x sub 2, I let y be 0, and then x becomes x sub 2. And if I do that process and solve, I'm just going to get this. X sub 2 is x sub 1 minus f of x sub 0 over f prime. Sorry, x sub 1 over f prime x sub 1. So notice what happens. To find x sub 1, I need x sub 0. So I can plug all that in. I get x sub 1. Once I get x sub 1, notice I need x sub 1 here, here, and here. Plug those in, I get x sub 2. Well, I'm not going to draw the picture. How do I get a better estimate than x sub 2? Well, I'd have to blow it up to really see what's going on. But I do the same thing. I find the tangent line at x sub 2, ride the tangent line up or down to the x-axis, and wherever I hit the x-axis, that's my next iteration. And each time that I do that, what's x sub 3 going to be? X sub 3 will be x sub 2 minus f of x sub 2 over f prime of x sub 2. It's the same formula, but it's building up, right? It's an iterative process. To get x sub 1, you need x sub 0. To get x sub 2, you need x sub 1, and so on. So we work our way through this. This is what is known as Newton's method. And so here it is in a nutshell. If we want to look at it, Newton's method is to approximate the root of the function f of x, or find when f of x is equal to 0, right, when its output is 0, when the graph crosses the x-axis. We choose an initial guess x sub 0 close to the desired root, and then we generate successive approximations by this recursion. And I want you to note that this recursion exactly comes from what we have in each of these cases. So to find x sub 1, we need x sub 0. So if I let x sub 0 be here, that means the n I'm talking about, this little subscript n, is 0, right? 0, 0, 0. Well, if n is 0, what's n plus 1? 0 plus 1 is 1. You see, this is giving me my first equation here. If n is 1, I'm getting this one, right? If n is 1, 1 plus 1 is 2, I get this one here. When n is 2, I get this one here. So this is a general way of writing all of them, right? We just continue this process. We just continue this process. Okay? So let's see how this works. Let's do an actual example and see how this works. Now I'm going to use technology to help in terms of calculating this. I'm going to show you with the graphing calculator at any rate, a quick way to do that. So let's find the unique real zero of the function x cubed plus x minus 4. I've graphed that function here. Notice this is not a quadratic function, so you can't use the quadratic formula. If we could use the quadratic formula, somehow it got blurry there. But if I could use the quadratic formula, I wouldn't have to worry about Newton's method. But this is not a quadratic; it's cubic, and we want to find the root accurate to 7 decimal places. Okay, so I can see here already the root appears to be between 1 and 2 when we look at the graph. We can estimate it that way. But let's go ahead and do this, and we're going to start with an initial guess of 1. I'm going to guess initially 1. Obviously that's not the 0. You might want to guess 1.5. I mean, if you had a choice to guess, 1.5 would probably be even closer. But this method very rapidly converges. Okay, and so now I'm going to use Newton's formula right up here. Okay, and in order to do that, I need the function f, which I have, but I also need f prime. Well, can we find f prime of x? Well, yeah, we can take the derivative of that function. It's a simple polynomial, right? That's 3x squared plus 1, derivative of 4 is 0. So there's our derivative. So now I'm going to plug in to Newton's method to find x of 1. So x of 1 means n is 0, so I get 0 plus 1 is 1. X of 1 is what? X sub 0 minus f of x sub 0 over f prime of x sub 0. Okay, so what's x sub 0? Well, that's 1. Minus f of 1. What's f of 1? Well, I replace x with 1 up here, and f of 1 is 1 cubed plus 1 minus 4. And what's f prime of 1? We'll plug 1 in here. I get 3 times 1 squared plus 1. Well, this is fairly easy arithmetic here, hopefully. I get 1 plus 1 is 2, minus 4 is negative 2 up top. 3 times 1 squared is 3, plus 1 is 4. So I get 1 minus what? A negative 2/4, a negative 1/2. 1 minus a negative 1/2 is 1 plus a half, which is 1.5. Okay? So there's x of 1, 1.5. And basically, if I want to look at the graph, what's happening here is you're starting at 1, you're coming up here to this point, and you're finding the tangent line, and you're riding that tangent line, in this case going up, passing through that point. And where are you going to hit the x-axis at? Right at 1.5, right? That's what it's saying. Our x of 1 here is going to be there, right at 1.5. Here's our x of 0, our initial guess at 1, and then we get to 1.5 after that. We're much closer to the root, aren't we? Much closer. Let's go to x of 2. So let's see what x of 2 would be. Well, that's going to be x of 1 minus f of x of 1 over f prime of x of 1. So what's x of 1? Well, we just found it's 1.5. And then it's 1.5 cubed plus 1.5 minus 4, plugging that into the original function, right? So replacing x with 1.5. And then plugging 1.5 into f prime gives me the denominator here. Okay, now obviously I can't do this so well in my head, cubing 1.5. Some of you maybe could do that. We're going to pull the calculator in here. What I'm going to show you is how you really want to do this so you're not tediously dealing with these expressions. Okay, and I'm going to show you a particular way. What I'm going to do is I'm going to start this way. I'm going to start with my initial guess, which is 1. I'm going to type in 1. Okay, and then I'm going to hit enter. And my answer is 1. Hey, how about that? Plug in 1, output 1. That's great. Well, what this does, though, too, is this stores your result. When you hit enter in the TI 83 and 84, you're going to store that into the answer. The answer comes up right here above the little minus sign here. ANS stands for answer. If I hit the second and then that answer button down there, right, it comes up as ANS, and I hit enter. The value of that is 1. The value of that is 1. It always has the value of your last operation. So notice since I hit enter on answer, 1 again is replacing, is back in answer. But whatever I get as a result, that will always be stored in this variable. So here's what I'm going to do now. Right? I'm going to take answer is x of 0, and I'm going to find x of 1. You already know it's 1.5, but I'm just going to show you how you would do this in practice. So I'm going to do x sub 0, which is answer, minus, in parentheses, right, the numerator of this, which is f of x sub 0. And what's f of x sub 0? Well, it's this, but again, I'm going to use answer instead. So I'm going to do answer what? Cubed plus answer minus 4. So I do answer cubed plus answer minus 4. That's f of x sub 0, close parentheses. That's the numerator of that. And then what? I'm going to divide that by f prime of x sub 0. So divided by, in parentheses, make sure you put in parentheses, the derivative, right, evaluated at x sub 0, which is answer in the calculator. So that's 3 times answer squared plus 1, close parentheses on the denominator. So there it is. You say, why did I go through all that trouble? We already got the answer here, right? Well, again, if I hit enter, let's make sure this indeed gives us 1.5. There it is. Okay? So, gosh, that's a lot to do every time. Okay. No, it's not, because we've done all the work. Now we're going to reap the benefits, and here it is. In addition to the answer key, in the 83 and 84, there's a very powerful button as well called the entry key. I think I might have showed some of you this before, but right here, entry, not the solve, but entry. And when I do entry, when I do second and hit entry, look what happens. It recopies everything I typed in. If you do second entry again, it'll enter what you did, what you entered in back before, just answer. In other words, it stores like, I think, 10. So if you ever want to go back 2 or 3 expressions that you entered to copy them, you can do that. Just keep hitting second entry and it cycles through all the previous entries. But now, this is the same thing I typed in, but notice now, what's the value of answer? When I hit entered here, what happened? 1.5. 1.5 isn't the answer. So now answer is 1.5. Answer is now x of 1. And when I replace x of 1, right, in all this stuff, that's this stuff, right? So when I replace answer with 1.5, I've got this stuff right here. So when I hit enter, I'm going to get what this is equal to as an estimate, right? Hit enter, and I get this. So let me write that out here. Again, it's approximation, but I'll just say 1.387096774. Do I have to write all that out? Well, it depends on how far you want to go. Remember, we want to go to 7 decimal places. So we've got to see when we kind of have honed in, if you will, on that solution. Okay. So let's go to x of 3 then. What's that going to be? It's going to be x of 2 minus f of x of 2 over f prime of x of 2. Right? Now I'm not going to do this part anymore. I'm going to go right to the calculator. And how am I going to calculate all this stuff? Oh my gosh, that's a bunch. Well, just by the entry command, because this is now right in the answer. So when I do second entry and recopy that same form, what's going to be plugging in for answer? 1.38. So I'm plugging in now. This is x of 2. I'm plugging in here to this. So I'm going to get x of 3. So what do I get when I evaluate that, my x of 3? Okay, there it is. So let's write that down. 1.378838948. Okay, and you can see, comparing from my previous answer, it looks like at least maybe the first decimal place is the same. They both have a 3, but then here's an 8, here's a 7. So I don't think I have 7th decimal place accuracy yet. So how do I proceed? Well, what's x of 4 going to be? Well, it's going to be x of 3 minus f of x of 3, or f prime of x of 3. So I got to plug this into the thing. How do I do that in the calculator? Just second entry, because there it is. There's x of 2, right, that we found. Sorry, x of 3 that we found going in now, and the output is x of 4. Let's write that down. Okay, and now as I move around here, look at, so here I said I was probably accurate at least to 1.3, right, the same, and then they differed here, which they match up 1.378. So it looks like we might be accurate to as much as 3 decimal places here. We want to be accurate to 7 decimal places. What do I have to do? I have to go one more iteration. X of 5. Second entry. Hit enter, and I'll plug in. I'll get x of 5. 1.3787967. I assume these next two would be zeros. There's nothing, just to match up with the number of decimal places we had before. But now look, what's that? 1.3787967. It looks like we've got 1, 2, 3, 4, 5, 6, 7, maybe even up to 8 decimal places. Certainly to 7. Okay. In fact, if I do this one more time, I'm not going to write down the result, but if I want to find x of 6, and I do this, look what I get for x of 6. There's really no change. So the changes are only way out here with these decimal places out here. We've kind of, with the calculator, honed in on the answer up to at least 7 decimal places. Right? So this tells me that the answer, the root to 7 decimal places, is 1.3787967. That's 1, 2, 3, 4, 5, 6, 7 decimal places. There's my estimate. So if you're a computer science person, I hope you see how you could program this formula, right? Basically what I did here, and just do a feedback, if you will. You get the answer and go back into that same formula, and you keep kicking out the next iteration. As you're doing that, you write the program to compare the previous one to see how many decimal place accuracy you got, and you continue until you are as accurate as you need to be. Okay, so that's sort of the basics of how Newton's method works. Okay, in the next video we're going to do a couple more examples just to get a feel for some other things we can do with this. But one thing I just want to say before we move on is this iterative process is not perfect. Okay. First of all, I hope you realize since I'm dividing by the derivative at x sub n, if it ever happens that the derivative at that point is 0, we've got a big problem, right? Division by 0 is undefined. But that should also make sense geometrically when we go back to this situation we were talking about, because if the derivative is 0, what's that mean? Well, we'll suppose I pick my initial guess x sub 0 for this one to be right at 0, right? If I come up here, what does it look like the tangent line looks like right at x equals 0 for this function f? If I draw the tangent line just touching, it looks to me like it's what? Pretty much horizontal, right? What we're supposed to do, ride the tangent line until we hit the x-axis. Okay, well, let's get on this tangent line. Let's go. Let's find the x-axis. Woo! Right? You're just going to stay at that height forever. You're going to go. You're never. It's going to fail. Right? The derivative is 0, and you see that in the formula. Right? Division by 0 is undefined. So it's certainly going to break down if you ever have a derivative equal to 0. So you do have to be careful, right? When we're choosing initial guess, you don't want to choose, around this vicinity. You want to get close to where that root is. Okay? But there are other examples of functions that cause problems. Most of the time, Newton's method is going to converge toward that 0. There are some pathological examples of functions we can give, set them up in certain ways where the method actually either zooms further and further away from the 0 that we're looking for, or we get caught in a vicious cycle sometimes where we're bouncing back and forth, and not really getting anywhere. So there are some situations like that. And there's some, if you're a computer science person and are interested in these methods, there's all sorts of numerical methods that you can look at for finding the roots of equations and doing other things. And there's modifications for Newton's methods to help with some of these issues. So we just want you to introduce this idea and see how it works as a nice little application of derivatives. So in the next video, I'll look at 2 more examples of some other things we can do with Newton's method.